So we can talk about the quiz in a couple of minutes just to give more people the chance to log in. Um, and other like stuff about the course. Like so kind of like the first big topic that we have to talk about is like the bisection method, which is how to solve equations. So that's kind of like what I'll start telling you about today. Let me see if I can, let me connect the iPad first. Oops, sorry. Okay, let's see. Um, is can you see you can see the iPad, right? Is that okay? Okay,
Yes.
perfect. Thanks. Good, thank you. Okay, so as I was saying, the first thing to talk about today is a bisection method, which I actually had mentioned a little bit about yesterday without calling it that. So if you remember, one of the things I was telling you yesterday is that this is kind of like an idea that was very common in calculus, right? That if you have like a continuous function on an interval, let's say you have like an interval A and B, something like that, continuous, then you know, some something that kind of like a classical problem in Calc 1 is to show that the function like must intersect the x-axis. The way that was like written back then is that you would like to show, let me say that this is from Calc 1. So that the equation f of x equals 0 has a solution on this interval, right? And the idea, the way that worked is that you would kind you know, in practice, like you would check, for example, like at the endpoints, or you would just try to find 2 points where the function would take different values of different signs. So like, for example, here at A, the function is negative, and at B, it is positive, right? So here, the function is negative, and this was positive. So you would say something like, well, f of A is negative, f of B is positive, and because a function is continuous, right? Uh, Plus the IVT, right? Like the IVT was just like this intermediate value theorem that I told you about last time, like, or reminded you about last time, right? So what the IVT would have to say is that, if the function is positive and negative at certain points, it has to kind of like go between all the intermediate values. So you have to go between going from negative to positive or positive to negative. It doesn't matter in which order that happens. And so eventually you have to be at least 0 once. Like you can be more than once, 1 times 0. Like, in this case, there are potentially 1, 2, 3 solutions, but the IVT at least guarantees um, that there will be at least one solution. So by the IVT, there is at least one solution. At least one number. Let's call that x star. I don't know. For which f of x star equals 0, which would be like a solution to our equation. Is that making sense? So hopefully this is kind of like just like a refresher because like you must have seen this like it's like a very common calculus one problem, right? To use a IVT to show that certain equations have solutions. Now, kind of like the idea, like from the philosophy of this course, is that it is very nice to know that there is a solution, but you kind of want to have more like control on the solution. So you want to be a little bit more precise, like about the solution. So ideally, and this is kind of like what we're going to start with today, like ideally, you would like to create like some sort of like method that allows you to find a solution, or if not find it, to get as close as possible, as close as you could to one of these solutions. So kind of like the idea or like the goal is to devise a method uh, that would get you as close as you want to the solution. Okay. So, and the bisection method is kind of like the most basic thing you could come up with, and that's what I'm about to explain right now, if that's okay. As the word suggests, like basically you kind of like chop off the interval in half at every single step uh, under some conditions, which is what I'm going to tell you about. So let me I'll try to write it kind of like as an algorithm, or like sometimes people call it like pseudocode, because like you don't this is not how you would implement it literally like on MATLAB or something, like, or like Python or whatever you're using to write the code, but it's kind of verbally what's going on. So let me just tell you about the bisection method. Okay. And let me draw like the graph again, but I'll draw something slightly easier just for me to kind of like, it doesn't matter how many solutions there could be, at least like there will be one. So let me just draw something a bit more simple where we're just going to be just one zero of the equation. So let's say maybe, I mean, yes, like it could happen just by kind of like chance. You'll see what I mean in a moment once you start writing it down, that you just happen to stumble upon the solution. If But it's not something you would kind of like expect most of the time. You'll see how it's like, just from like the construction, you'll see that that would be like very unlikely. You know what I mean? Um, so, like in general, like you wouldn't count on it, but like, yeah, it can happen by accident on occasion. That's how I would say it. But I'll kind of like write it down now, and you'll see why that's kind of like a bit more clear. So again, like let me just put something like this, and I'll show you some like an animation in a moment. But so kind of like step one, and that is kind of like your starting point. Um, Let me use this like steps with different color. Step one is that you have to find, you know, uh, two values A and B. where the function has like are like they distinct sign, like the values of the function are of opposite signs. So either like positive, negative, or negative, positive. So you find two values A and B where either f of A is positive and f of B is negative, or f of A is negative and f of B is positive. Okay? So basically, what I'm saying is that you find A and B where like negative positive or positive negative. In this, like the diagram, how I drew it, it is f of A is negative and f of B is positive, but like it will work kind of like the same. It will work fine if you had it like if it had been done in reverse. Um, there is a nice way of writing this down because positive positive is positive times positive is positive. Negative times negative is positive. So the only way for the signs to be opposite is if they multiply. When you multiply them, you get a negative number. So like you can write these two conditions as equivalently. What you want is f of A times f of B to be negative. Right, because again, like the only way that could happen for the product of two numbers to be negative is that if they have distinct signs, right? And that is like a condition which presumably, you could check. We're not going to get too much into the weeds of how like computers deal with like arithmetic operations. Like if you're reading the book, chapter one has some discussion about that. So like, of course, like, because like the computer won't store like digits with infinite precision, that just cannot be done. Then there's always some approximations and things that need to be happen. But so we're kind of like stating it in the ideal world, but like there's some like practicalities that do come in mind from time to time, um that you would also keep in mind when you're writing it down as a code, and the reason, if you happen like and again, I'm assuming here that like you don't know how to find a solution, because otherwise, like if one were zero to begin with, then you would be done. Like this wouldn't like make sense. Like so you're kind of like assuming, that you just like start with one value being negative, the other value being positive. Okay. Um, so far so good. Is that making sense? Uh, and then step two is kind of like this is where you're trying to approach this is where you're trying to approach the zero in a more precise way, because this is where the zero should be, right? But kind of like the idea is that you kind of will have the interval. Okay, so you will divide the interval into two subintervals. So into two subintervals of the same length. Okay, so there is a formula for the midpoint of, like, if you have two numbers, right? If you have two numbers, then the distance of the interval, or the length of the interval, I mean, the length of this interval would be b minus a, right? So the midpoint, let's call this midpoint x1. Then the midpoint is going to be a plus v minus a over 2. Okay. Like you just add half the distance, right? That makes sense. And then just give, if you can like work it out, if you like, you can also write it as a plus b over 2. That it looks a little bit more symmetric. So it's kind of like nicer, uh, like as a formula to just have it this way. Um, okay. So the two potential intervals, right? So like the two intervals that you get are, so the intervals, sorry, let me call them subintervals. Okay. Um, is that so far so good? Is that making sense? Um, and then all like two, like basically there's only two things that can happen. If f of x1, if the midpoint happens, if the function happens to be zero at the midpoint, this is good, right? This is all over, right? So so here like the subcases. If f of x1 equals zero, that that gives you the value that you were after, so you can stop like the process, right? Like you can stop. And that actually answers like the chat question, like about like whether you actually can ever get like the actual solution. Yeah, that could happen like if by coincidence, when you subdivide, like the midpoint happens to be the where the zero occurs. But of course, like that is not what you would expect in practice, right? That would be like a very lucky coincidence, right? So that is like we kind of like when I'm writing it down, I'm assuming kind of like the worst case scenario. So the worst case scenario is where this does not occur. So so if f of x1 is not zero, that means that it is either positive or negative, right? And so you just keep the sub interval where the endpoints once again have like the opposite signs, right? Because yeah, like sometimes it's actually referred as that's a good comment. Like that's sometimes referred as binary search. It's kind of like the same philosophy. Yeah, yeah. Um, and so of the two sub intervals, you keep the one where the endpoints again, where the function has like opposite signs at the endpoints, right? You keep the one where the function um, takes uh, has you know, positive and negative values. Let's just write it like that. Is the idea making sense? So just to kind of like draw the picture a little bit. Uh, sorry, just to grab copy paste the graph. I'm about to show you like an animation just to make it nicer. But let me do it here to illustrate. So this was like the original. Uh, that was the original interval. Um, I have no idea where the midpoint between these two would be. Let's say it's kind of like a bit. Let's say the midpoint. What I'm calling. I don't know. Let's say that what I'm calling the midpoint is somewhere in here. I mean, it doesn't look quite correct, but like, just bear with me. So if that's the midpoint, right? Like here, like it would have been negative, negative, right? Like this sub interval. Um, let's use different colors. on this subinterval, the endpoints would have been both negative, so it's not good for the like that is not the correct subinterval, right? The subinterval that you would keep is the one, this one, because here this is like negative and this is still positive, right? So like you of the two, you would keep the one that still has like the property uh, that like the endpoints, the function has like different signs at the endpoints. And then step three is to like sometimes you would call this iterate the process. Like you kind of like just repeat the process, kind of like run it through the algorithm again, but with this new sub interval, right? So you apply. Let me just kind of like write it this way. Apply um, to this sub interval. And I'm about to write a couple more things about this, but that's kind like that is really like the summary of the idea, right? So you kind of like always cut it in half. So like like the length of the subintervals is like shrinking by a factor of two. Like the new subinterval will be half the previous step. In the worst case scenario, right, where like you don't happen to stumble across the zero by accident, right? But and so kind of like you kind of like just intuitively would expect that that will converge to the solution just because you're having cutting in half like every subinterval, right? Is the idea making sense? Is that okay? Questions up to this point? So let me show you like an application. Sorry, not an application, like an animation, and then I'll say a couple more things about this, kind of like more writing this down in a slightly more precise way. Uh, Let me see if I can stop sharing my screen. Mhm. This is the one that I want to share. I think this is yes, I think this is a can everyone see kind of like this demo like animation from demonstrations wolfram.com that says x squared over 2 minus 1? Uh, yes, okay, good. By the way, like I don't know if you have used that. I'll, at least I'll mention it because like I do like demonstrations Wolfram. So Wolfram, I mean, you probably have used Wolfram Alpha for sure, but like Wolfram also has kind of like I don't know, a second side called like Wolfram Demonstrations Project, which is very nice because there you can find tons of like animations for different topics. Which are kind of like ready to go, so you don't have to write anything. So that's kind of like how I found this one. I just typed here in the search bar bisection method, and like the one that I'm going to show you is one of those. But if you ever like are learning like a new concept, and one, it's always like just useful to see what it's out on Wolfram demonstrations because usually people like put some effort into making them. So for example, here um like some of the options that they give you, it's like you could do it with x squared minus 1, which of course you know how to find a zero for x squared over 2 minus 1 because it's like a quadratic equation. So you could actually find that explicitly, but just pretend that you didn't know how to take square roots, right? If you didn't know how to take square roots, and if you apply the bisection method, then this is precisely what you would do. Like you have like an original interval, which is roughly from 0 to 2 in this case, like the way I chose it. So that's like original step. Step one is kind of like the original interval. Then step two, uh, you cut it in half, right? And so you kind of like I think hopefully you are able to see kind of like this like smaller horizontal line that's being drawn. And that just represents like the new like the sub interval that you keep, right? Because it's similar to the one I drew on the iPad. Like if you had kept this half, then it's negative, negative, which doesn't work, right? So now you focus on this half and then apply the method one more time. And then like now the half that works is this one, right? Because it's still negative, positive. And it's nice like in this animation because like the vertical lines, these dotted vertical lines tells you kind of like the walls on the of the interval. And then you kind of like keep applying the iteration algorithm, right? And then it kind of goes on. I mean, at some point, like it will become super easy to see. Um, but this gives you like a nice illustration because what you see, like if you just focus on the intervals themselves, let me see if I can zoom in here, if that makes it easier. If you focus on the intervals themselves, you see that every interval, that the new interval that you generate is inside the previous one. So sometimes in mathematics, those are called like nested intervals because one is inside like the other. It's kind of like these Russian dolls, if you have ever seen them, when you open one and you see a smaller Russian doll, and then you open that one and there's like a smaller Russian doll. So this is kind of like a sequence of intervals that are shrinking one inside the other. And so that's kind of like the nice the picture to have in mind um, in this case. And the other thing that is like if you see at the endpoints, right? The left endpoints, like that's here's another thing to notice. Like this is the original left endpoint, then this is the next left endpoint, this is the next left endpoint, this is the next left endpoint, the next left endpoint. So like the left endpoints are kind of like moving to the right. Sometimes they get stuck, right? But the left endpoints are kind of like moving to the right. And if you look at the right endpoints, right, this is like the original right endpoint. This is a next right endpoint, next right endpoint, next right endpoint, next right endpoint, and then it kind of moves to the left. So kind of like what's happening is kind of like walls, kind of like approaching one another. So the left endpoints are moving to the right, and the right endpoints are moving to the left. So they're kind of like almost like in a collision course, and that's like where they collide at infinity. That would be the zero. Is that making sense? So I'll write all of this down so that it kind of a bit more precise. But hopefully, it almost makes it obvious that this should converge, right? I'll still say a little bit about that, but there's almost it feels like almost no way for this not to converge, right? So like the way that it's designed. Mm. Maybe while I'm still on the computer before I write that down, I imagine like probably everyone already logged in. So I posted some problems, which I'll keep updating. So I'll add some more problems today. But so as I said, tomorrow we'll have a quiz. So for the quiz, you can just focus on the first two problems because again, it's just for I don't want to ask anything from like the day before. And so on yesterday's class, we didn't cover that much. So just look at problem 1.1 and 1.2, I still posted like some answer key for some of them. But and then that quiz, I'll just do one of those, like or maybe both, like depending. Like I may put both, but it's just kind of again like the first quiz is just for you to have something to do. So just to practice how the responders thing works. So like it will be this based on these two problems. Like and the rest like you don't have to worry about for now. And I will still kind of like I keep adding more stuff to the PDF. Then what I did, which I said as I said yesterday, the quiz will probably be like I'll stop the class tomorrow around noon 12 p.m. so that or a bit earlier so that you can work on the quiz. So the kind of like the way the quiz will work in general, and I created an assignment for you to try. Like so, after we're done with today's class, at some point of the day, just try. I'll send an announcement about this to remind you. But just go to this quiz that says responders practice. So it's not graded or anything. It's just for you to kind of like try it out because in order to take the quiz, what I was telling you yesterday is that you have to kind of like use responders and lockdown browser. So you have to download it and like so try to do that. we're just today, so that you have like some acquaintance with how it works, and then as you can see, like the question is like it's not even graded. It's like a silly question. It's just for you to write something on a piece of paper, so that you can also practice writing it on a piece of paper, showing your work once you're done with the quiz. Because like usually, like after you before you log out from Respondus, it will ask you to show your work so that it takes a kind of like a quick picture, and then there will be like there is a separate assignment where you would upload the paper that where you answered the question. So you can upload it as a PDF or like a JPEG file. Um, and that's kind of like how like the quizzes will run, and also how the exam will kind of like operate. So it's kind of like useful to try to get comfortable with this um, before like like before the exam, which is really when it's like the important date. Um, is that making sense? So, but like you can attempt this as many times as you want, so that you can just like get used to how it works. Um, any questions about this?
So we do this quiz practice like today just to get the hands on before
Yeah,
tomorrow's quiz.
I mean, yeah, you should, as long as you do the practice quiz before any time tomorrow's class, like that's fine, because the thing is that you will probably have to download lockdown browser if you haven't done it before. So it's better to do that uh, today or before class, so that when you're taking the quiz tomorrow, you don't have to download it, because that will kind of like maybe take 5 or 10 minutes. I don't know how long it would take you. But yeah, you can do it at any point of the day. Well, I guess I have it like at uh, wait, at what time do I have it as a deadline? I have it at 11:59 p.m. So in principle, you should try to do it before 11:59 p.m. But I think you can even access the quiz after that. It just will say that it's like a late submission, which doesn't matter because this one doesn't count for anything. Uh,
When we write our answers, can we at the end when we're finished, can we use our phone to use the
oh
AI
yeah, yeah, yeah.
format?
So once you're done with the quiz, writing it, like yeah, you can take your phone to take a picture of the work, and then I don't know, airdrop it to your computer to create like the PDF, if that makes it easier for you,
Yeah,
or
I
even
don't.
from the phone.
Yeah, I
Yeah,
don't
yeah.
have. I don't. I don't use app. I mean, like iPhone or I use like Pixel and Microsoft, and they are not compatible. So I think I have. It takes me a little bit longer
I
to
mean, I think
transfer the file.
you should also be able to upload it from on the phone. I think even if it's not an iPhone. Well,
Oh
that's
yeah,
kind of
yes.
like
I use the Canvas I have on my phone.
right. Yeah, yeah,
Oh,
yeah,
I
yeah.
do
You
that.
can use a yeah, yeah. You can use a canvas on your phone, and that should be fine
Okay,
as
I got
well.
it. I
Yeah.
got it. I got it. Okay, cool.
But I mean, but that's kind of like the thing for you to try today. That's why I want everyone to try it, because if it's not working, then you can let me know, and I'll keep that in mind, and then we can try to find like a workaround. But yeah, Canvas. If you have the Canvas app on the phone, I think that should also work fine. So, but yeah,
Okay.
if you try it and if you're having issues, you can like let me know, and we can see what's going on. Um, is that okay? Anyone else? Any other questions? But yeah, I'll send an announcement after class, kind of like well, I think when you try to click on the quiz to try to take the quiz, it will force you to 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 download the lockdown browser. So like the quiz itself should take you to the place where you will do the lockdown browser. And then in terms of the iPad, no, like the idea is for the quiz to kind of like be done on a piece of paper. So because otherwise like there's no way to kind of like anyone can have anything on the iPad. So yeah, you do have to have like some blank paper where you write it down. But yeah, like in terms of downloading it, I think when you try to access the quiz, it will tell you, oh, you have to download Lockdown Browser first, and it will take you to the link where you can do it. Okay, perfect. Let me just now that I made this like a small detour into the quiz stuff, let me go back to the iPad. So what I was saying in terms of like the picture to have here. So like kind of like the animation, what it shows is kind of like the structure of the intervals. So so like I'll just draw like the intervals themselves and not worry about the I will just draw the intervals themselves and not worry about the graph because I just want you to notice like this thing that I was saying. So kind of like the idea is that whenever you have the interval, let me make four copies of it so that you know. So maybe in the first step, maybe in the first step, the interval that you keep is this one. Okay. Then in the next step, the interval that you keep, oops, sorry about that. In the next step, the interval that you keep is this one. And then in the next step, the interval that you keep is this other one. So it's always half the previous one, as you can see. So if you want, just to like, oops, sorry about that. Just to have some notation to be a bit more consistent, you can call the first interval, like the original interval, interval one. Okay. Just to use a little bit of sequences. Okay. So like you just call instead of calling the endpoints A and B, you call them A1, B1. Okay. Then in step two, right, when you make the first subdivision, this would be called interval two, and then the endpoints would be called A2, B2. You see. And then in step three, like the next subdivision would be interval three, which is A3, B3. Okay. And the fourth step, like the fourth interval, would be A4, B4. So here's like A4, B4. Here's A3, B3. Here's A2, B2. Oh, sorry, B2. And there's this A1, B1. Okay. So kind of like what I want you to notice is like the property that these intervals have, like the two main properties that they have. So in general, that you know the intervals are called in equal to an bn. And so what the two main properties that they have is that the length of the nth interval is half the length of the previous interval. So property one is that the length of in is one half of the length of the interval in minus one, right? And then kind of like what I was mentioning from the animation that the A's either stay the same or they always move to the left. The A's. So what I mean by that is that A1 is less or equal to A2, which is less or equal to A3, less or equal to A4. So one way to think about it is that the ANs form an increasing sequence. That's kind of like the naming calc too that was given to that. And the B is kind of like working the reverse way, right? So the first B, they're kind of like they're moving to the left. So what I want to say that is that B1 is greater or equal to B2, greater or equal to B3, greater or equal to B4, and so on. So the B ends are decreasing. They're moving to the left. Is that making sense? Is that okay so far so good? And so kind of what happens, I believe I actually mentioned this like yesterday. One of the things you may have seen from Calc 2 is that if you have an increasing sequence that's bounded, then it converges. Or likewise, if you have a decreasing sequence that's bounded, it converges, right? So, oh yeah, 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 of course. So what I'm saying is that if you notice how the lengths are like the intervals are generated, kind of like that's how I was trying to do it this way. The length of the next interval that you choose is half the length of the original interval, right? So the purple interval has half the length of the red one, and then the green one is half the length of the purple one, and then the blue one is half the length of the green one, right? So because you're kind of like always choosing the midpoint to kind of like split the interval into two halves. So is that making sense? Like what I mean? So you always cut in half the interval and just keep half of it. Let me see if I understand. But the positive and the negative. Oh, right. Yes, of the right. Why do I keep this half? Like, for example, why did I keep this half? Because this is where like the endpoints had different signs. Why did I keep this half? Because this is where the endpoints had the distinct signs. Yes. So I can add that as property three. That's a good comment. Yes, that the way this is being chosen is that at the endpoints the functions still have like distinct signs. So. But that is that fact, right? Uh, two can be different if it was the other way around. Well, it depends on what you mean. Oh, no, even if you had chosen, like that's the thing, like that like the fact, right. Even if you had chosen, like imagine that you had chosen, for example, uh, this other half. Even if you choose this other half, it's still the case that the endpoints of A, the left endpoints, the leftmost endpoints are kind of like increasing. That's kind of like the nice thing of the nesting. It has nothing to do with the sign. So if you are always think about it, if you took like a string, right? If you chop it off, always cut in half. If you keep track of the halves of the sub intervals, you'll see that they kind of like they do kind of like the left endpoints kind of like move to the right and the right endpoints move to the left. That is kind of like a property of this nesting thing of the intervals. Is that making sense? Okay, and then yes, that's a good point. You could be if there had been like four solutions inside this interval, the most you can guarantee with this bisection method is to find one of those, right? Because you could like totally skip the others by this method, right? That's correct. Yes. So it doesn't it just it's just like a way to produce one of the solutions that could be within this interval, right? And then what happens is that because of what I was saying yesterday is that you have this increasing sequence which is bounded, so it has a limit, and the so let me write that down next. And this is kind of like the punchline. So this is like the important part. So the ANs are an increasing sequence which are bounded. So they converge. So they converge, and you can call the let's call the limit x star. And likewise, the BNs are decreasing and bounded, and so they converge also. Likewise, which are bounded. So they converge. Kind of like the nice thing, they converge. The nice thing is that the limit of both is the same, right? Why is the limit of both the same? Because the length of the intervals are going to zero, right? So the distance like is going to zero. So like between the ANs and the BNs, so like they cannot converge from to different things. So let me make that as a remark. Notice that it is the same limit since the length of the intervals is going to zero. So like the fact that they kind of like the intervals are shrinking, everything is kind of like collapsing. And that's just why that only leaves you one thing at the end. Are we so far so good? Is this making sense? So far so good. Any questions? So the last part of the claim, I still okay. So we just found a point in the limit that kind of like is at the very end of all these bisections, right? So you keep subdividing, 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 and in the limit there's this point, right, which I'm calling x star. What you would like to say is that x star is a solution to the equation, right? So my claim is that f of x star should be zero, which may seem obvious, but you still have to kind of like say something about that. So this is like the desired solution. And why is that the case? So the reason why that's true is because remember from like property three that I wrote, uh, where is property three? Like the endpoints had the property that like they multiply, they had opposite signs, right? So uh, now maybe you had not seen it before, but there's a nice thing that you can do with limits. Actually, when you have an inequality, you could also apply limits to both sides of the inequality. The only thing that happens when you apply limits to both sides of the inequality is that it can become, it stops being strict inequality. So it becomes like, for example, in this case, less or equal to. So, so the only thing that can go wrong is that like the inequality is preserved, but you can get like an equal sign. So, and the way limits work, the limit of a product is the product of limits. Okay. And because the function is continuous, so what it means to be continuous is that it's like f of x star because an is converging to x star. So because f is continuous, since f is continuous, this gives you f of x star times f of x star. That has to be greater or equal to zero. Sorry, less or equal to zero. But that means that the square of f of x star has to be less or equal to zero, and that can only happen if the square of a number. There are no complex numbers in this course, right? So at least maybe we may do some applications with eigenvectors, so maybe they will reappear. But for now, everything is real valued. There are no imaginary numbers. So when you square a number, you get something non-negative. So that forces like this to be zero. So it's like a very clever, like it's like a very elegant argument. You see, it's kind of like also it's like a good argument because it shows you like kind of like the idea is very obvious, right? Like it's very plausible what's going on, that this method should work. But when you kind of like fill in the details, you do realize, oh, there are actually some interesting things that you had to realize, like you had this sequence that is shrinking of intervals, and the endpoints are moving to the left, and the other endpoints are moving to the right. There are there's like a bunch of stuff going on. So even if the method is kind of like obvious that it should kind of like work, when you try to kind of like fill in the gap, there's still kind of like something to be said for it. It's not as silly as it may seem. Um, is that making sense? Okay, let's take a quick break because the next topic I'll maybe talk for another like 30 minutes or so. So let's take a quick break um, so that like we can start the next topic fresh. It will be related to this type of problem, but it's a different thing called the fixed point theorem, which is a very important thing. So just to kind of like start with like let's take 5 minute break. Uh, Say 11:30. So at 11:30, I'll start telling you about the other stuff. So I'll be right back, but I'll also be stay here like just answering questions if someone wants to ask me something specific. I'll start recording. I'll be right back. Done already? No, I made a break. No, get myself. Yes. Would you? Sorry. Did you ask something?
Any graduate courses involved?
Sorry. Can you repeat?
Any graduate level courses involved? Involved
A
in
graduate level
teaching
course. If you're asking me if I'm teaching a graduate course in the
Yes,
fall,
yes.
or no, I'm teaching. Up maybe send like an announcement later on. I'm teaching like a topic course, on tensor networks. But which can actually count as a graduate course. It's Math 495. Um.
I, yeah, that that course was shared with us from the
Oh yeah, yeah, yeah.
director. So I
Yeah,
think
yeah,
I'm
yeah,
going to run that. I asked the director, Mrs. Dr. Conconi. She said it will count for graduate credit.
yeah. Uh, well, so at least in math, I was asking about it, and they told me they would count it. Let me see, but they're still figuring out those details. Where is the syllabus? Where did I write the syllabus?
So is it? So I'm thinking about enrolling in it because I already confirmed with the uh, Dr. Conconi, and she said it will count for. She said it will count for a master's uh, requirement, but in
Uh-huh.
terms of attendance, there might be a chance because I already spoke with my other professors
Uh-huh.
from the Transit and the graph theory, they're both
Hmm.
graduate courses. And they agreed for me because I have a medical problems, I might not be able to come to the campus for fall. And if
I
I
see.
were to enroll in your class, I think everything is based on the theoretical homework assignment. And is there a
Yeah,
possibility if I enroll?
yeah. You should email me. I think that should be fine because I'll also record it. So even if you cannot come to campus, you can still watch the recordings, and
That's perfect. That's perfect.
Yeah,
And
yeah, yeah. Uh-huh.
in terms of the enrollment, so there are some courses that might not be in session because of the low enrollment for the
Hmm.
graduate courses. So your course is still gonna be in session, right? If it's still
Yeah,
gonna be in
yeah.
session, then I come
Right
to the
now,
graduate department and they enroll
mhm.
me.
Right now it has like 16 students, so it's fine. Yeah.
Okay, okay. So tomorrow I'm gonna email the Dr.
Oh, okay.
Kakuni. I'm gonna see you. I'm gonna CC you and Mrs. Kathleen. So I'm gonna email her and I'm gonna CC you and the secretary so everybody knows that they can enroll me in
Okay,
495.
perfect. Yeah, yeah, sounds good.
Thank you so much. Thank you. Thank
Okay, good. Okay, I think we can start again. Um, okay. So, what I'm the next topic, which is related to this one, but it's a little bit more interesting for reasons like I'll try to illustrate today. It's called the fixed point theorem. Um, So what I'll do kind of like for the next 30 minutes or so is to give a bunch of examples, and then we'll continue talking about tomorrow. Because again, as I said, I don't want to kind of like, 2 hours is a little bit too much time for a class. So like I'm trying to kind of like keep it under control, the amount of time. So I will kind of like just do a bunch of examples today, and motivate the idea from different like areas. And then tomorrow we'll kind of like talk about it in more detail. But so the next topic is called the fixed point theorem. So I'll start kind of like with the definition, which is not super precise, and then I'll kind of like be making it a bit more precise. So, um, if there is a point, um, let's call this point P, just to distinguish it. Distinguish it. Well, I'll keep calling it X star, I guess. Okay, so a fixed point, basically what it means is that when I give you a value for x, and if you apply the function to that particular value, it returns the same number. So the function does nothing to that particular number. So the function doesn't. Okay. So maybe it's good to have like some examples first before I say more things about that. So here's like an example of like some fixed points. So and now I'll draw some pictures in a moment. So imagine that the function is f of x equals x cubed. Okay, the cubic, right? So oops, sorry about that. Uh, Let me draw the graph. So this is the graph of the function. So what would be a fixed point for this function, right? So it basically is a point for which x cubed equals x, right? So can anyone think about a number that equals its cube? What could that be? Yes, there are three options actually: 0, 1, and -1. Right? Very good. In fact, like I mean, if you like, maybe the notation with the star is a bit annoying. If you are trying to solve this equation, right, it's the same as x cubed minus x equals 0, right? Which, if you factor out an x, gives you x squared. X times x squared minus 1 equals 0. So x times x minus 1 times x plus 1 equals 0, right? Um, And so that from there you see like the three options, right? So the options are 0, 1, or -1. Very good. Um, okay, let's see. Um, the cubic has those three particular fixed points. Um, Geometrically, here's one way to think about it. Um, like geometrically, what's going on is that if you look at the graph of the function, right? If you had like a particular function, um, not just necessarily x cubed, you have like the graph of a function y equals f of x, right? And then you have the identity line like y equals x. Right. So from this perspective, what is a fixed point? A fixed point is like the intersection corresponds to like the points where the graph of the function intersects the line y equals x, right? So a fixed point here's like a fixed point. Well, I mean, the point is like refers to the x value, but they're the same because like of how it's built. So in this case, like a fixed point is where is where um, The graph of the function intersects the line y equals x. Is that making sense? Um, if you look at it from that perspective, right, it kind of makes sense, just in terms of graphs. Okay, so maybe sometimes there won't be any fixed points, other times there could be fixed points, right? Um, it could be like a hit or miss. And so kind of like the goal that we were kind of going to start talking about uh, for the next couple of minutes and also tomorrow is kind of like to think about what conditions you could impose, you could ask of the function so that it guarantees that there is a fixed point, right? So kind of like the goal. That will guarantee the existence of a fixed point. Okay. Before I kind of continued, kind of like telling you what kind of like are the conditions that you usually go for, it's useful to see other examples outside the one we will be focused on. So kind of like the focus of this type of problems will be for functions of one variable, but it's kind of like useful to see that the concept of fixed point is like more like present, and it's not just about functions. Okay, so of one variable. So just kind of like to give you some examples of other fixed point, like of like that this is definition. Um, I think I mean everyone has taken Calc 4, some differential equations. So for sure everyone has seen like matrices. So for example, let's say you take a square matrix. So in this case, a vector is a fixed point of the matrix. So you see, it is basically the same, like the matrix version of like the fixed point definition that I wrote for a function. But these type of vectors are actually really important. I don't know if anyone can remember if a vector satisfies this. There is a special name for this vector. Does that ring a bell? Let me give you a hint. Yeah, again, vectors, right? So compare with a v equals lambda v, right? So the only difference here is that I entered lambda equals 1. So a fixed point of a matrix is an eigenvector with eigenvalue 1. So for a matrix, a fixed point vector is an eigenvector with eigenvalue 1. The eigenvalue has to be one because literally, like the idea of a fixed point is that you do nothing to the vector in this case, or the point, right? So it leaves it alone. Or the other option, or it could also be the zero vector, because if you remember, the zero vector is not considered as an eigenvector under any circumstances. So, but A times the zero vector is also the zero vector, or X would be the zero vector. So you see, like for example, that is if you take the definition of a fixed point to something like linear algebra, that coincides with the idea of a eigenvector with eigenvalue one. And I don't know if in differential equations, like you talk a little bit about dynamical systems and things like that, but kind of like the idea is that if in the case of like an eigenvector with eigenvalue one, kind of like nothing happens to that. So it's kind of like an equilibrium point in a sense. If like the matrix is kind of like representing like how something evolves over time or things like that. So it's like a useful concept because like it does appear like what we're talking about right now does appear in other places that's just not like function like beyond like functions of one variable. You see, like it has like many other applications. And there's like actually like a famous theorem, which I'll just mention it, but because like it's an interesting theorem, which is called the Brouwer fixed point theorem, uh, which we won't do because like that's way more advanced. But it's just kind of like useful to mention it so that you see that it's used in many other places. Another example of this is like the Brouwer fixed point theorem, which basically says like take a disk on the plane, for example. So imagine having like a disk on the plane. So you have like a two-dimensional disk. And like imagine you had like a function that just moves points around. Okay, so you could take like a function uh, that takes a point on the disk. Let's call that point x, and moves it to some other point on the disk, which I'll call f of x. And takes another point on the disk and moves it to another point on the disk. So you have like a function which like moves the points on the disk around. Here's like one way you could do that. Like you could kind of like rotate it, right? So if you have like a disk, right? If you have a disk, you can rotate the disk and that kind of like moves the points around, or you could reflect the disk about like an axis. There are many different things that you could do. So you have like a disk and the function moves the point x to a different point on the disk. So the fixed point theorem of Brouwer says that no matter what that function is, provided it's continuous, then like there's always a point that kind of like remains in the same spot. Like you must always fix at least one point. Uh, so if f is continuous, uh, it always fixes at least one point. Uh, And this is actually something that is used like even in economics with like this Nash equilibrium. If you have heard about that, like if you want to show like there's certain things like like reach some sort of equilibrium, it uses like at some point like a version of like this fixed point theorem. I mean, there are more complicated versions. Like this is not the only one, but it is like a very powerful idea. Like it just like it does appear like in many different places in mathematics. So. But again, like it is not like our focus, but it is still useful to see that it does like it is like a very useful concept to have in mind. So when you're trying to find fixed points, like that is like a very important problem. Uh, like here's another example from differential equations, actually. Um, well, if you remember, if you have like the exponential has like this funny property, right? That if you take the derivative of the exponential, it gives you the exponential itself. So there is a sense in which the exponential function is a fixed point of the derivative. I think in differential equations, you kind of like talk about the derivative a little bit as an operator. That's probably how you called it at some point. So you would say that the exponential function is a fixed point of the derivative operator because like the derivative operator does nothing to the exponential function. Okay. And this is actually how it's related. This topic of fixed points is very much related to differential equations because sometimes when you want to show that certain differential equations have solutions, you kind of like rearrange it as a fixed point problem, and then you have to use something that would guarantee that there's like a fixed point. But that is actually like one way you can do show existence of differential equations by like setting it up as a fixed point problem. Um, So, I mean, these are all very distinct examples. We're just going to do the baby example, the baby example being functions of one variable, so nothing too crazy, So, like, what I'll focus on is some functions of one variable, but it's still kind of like useful to kind of like see that there's like a bigger context where all these ideas get used to. So, like, the fixed point stuff, it is really one of like the most useful ideas in mathematics. Like, it does like appear in all over the place. Um, but our focus will be for functions of one variable. Okay. So like all these examples is just like for motivation. So, so what it turns out to be the case, again, we're like, just to go back for a second to what I was saying, the fixed point, if you look at the fixed point equation, uh, geometrically it corresponds where is this picture? Oh yeah, here it is. Geometrically it corresponds to like the graph of the function intersecting the identity line, right? Like the y equals x line. uh so what ends up turning out in practice is that a useful condition that will guarantee that there's a fixed point uh will be related to this idea of the function being a contraction. Okay, so that's kind of like the last thing I'll say today. um So what will turn out to be useful is the concept of a contraction. So contraction, it kind of like means what the name says, right? If you say you are contracting something, right? When you say you contract something, that means that you're shrinking it, right? A contraction is kind of like something that shrinks it. So I'll kind of like give you like a definition of what I mean by a function being a contraction. So the definition is a function is a contraction with constant uh, k. Well, let's just call it like a contraction. It's a contraction on an interval a comma b if there's a constant, which usually is called k, less than one, well, positive constant. So k is between 0 and 1, with the following property, with, and I'm about to draw a picture, don't worry about it. So what that means, like, let me see if I can draw a picture because otherwise it's a little bit too technical. So what I'm saying is that you have an interval. Let's say you have an interval a comma b. Let's say you have an interval a comma b. So what the function is a function is a contraction. What happens is that if you take, let's say, 2 points x1 and x2, oh, for any 2 points, if you take any 2 points on this interval, okay, the idea is that if you take any 2 points between this interval, the distance between their f of x1 and f of x2 is less than the distance between x1 and x2. So kind of like the function shrinks the distance between the points. Okay. So like the way to say this is kind of like the distance separating x1 from x2 is larger than the distance separating f of x1 with f of x2. Let me say that in words here. So Right. Yes. Right. Like it's allowed to multiply. It's by a fixed factor, right? So so for example, if k is one half, that means that the distance of the images is at least for sure less than a half between the distance of the points, right? Um, so, but that because the k is between 0 and 1, so it kind of like shrinks it. You see. Um, so yeah, like let me illustrate it by with k equals one half. So for example, if k is one half, if k equals one half, what I'm saying is that the distance between the images, right, is always less than half than the distance between the original points you started with. Let me put the k with a different color just to make it more clear that you know. So when you compare like distances in the image, like it kind of shrinks, but by this factor, like so it's kind of like it contracts it by like some predetermined factor. So like the k could be one half, or it could be one third, or one fourth, etc. Like whatever the number happens to be, it just has to be less than one because that guarantees that it kind of like shrinks it. Um, is that making sense? Let me give you an example, and I will be done with this. And tomorrow I'll tell you when this happens. But let me at least, I feel I should at least end up with a more concrete example so that it's a little bit more clear. So let's take like the quadratic formula, like f of x equals x squared. Okay. And that would be the last thing I write today. Okay. Let's say I look at this function, f of x equals x squared on the interval. Let me see if this will work. 0 to 1/4. Okay. And I can even draw the graph for you. So this is like the entire graph of the function, right? But I'm just looking at the function restricted to the interval 0 1/4, right? So my claim is that if you choose any 2 points on this interval, right, and you square them, right, like this is where x1 squared would be like, and this is where like x2 squared would be like, right? If you square their values, so despite what the picture despite the appearances, this distance will be less than this distance downstairs. Okay. So my claim is that this function is a contraction on this interval. It's at least I want to make sure that the statement is making sense. Is that making sense? Like what I'm trying to say? I'm saying take two numbers between 0 and 1/4, right? Take any two numbers you want between zero and 1/4, square each of them, square each of those numbers, and the distance between those two new numbers, like the squares, will be less than the distance you started with. Okay? Is the same in making sense? Now, what is the distance between the squares? Like that's kind of like the fun part. Like this is like what numerical analysis is a lot about. Like you have to find what people refer to as estimates. So you have to estimate the difference of many things. Like so what is the difference of the squares? Like it would be what is f of you know what is f of x2 minus f of x1, right? What that is the distance between the images, right? That is x2 squared minus x1 squared, right? What is that? This is a difference of square formulas, right? So this is x2 minus let's put it like this, x2 plus x1 times x2 minus x1, right? That is how difference of square works. And the absolute value, if you remember the properties of absolute value, the absolute value of a product is a product of absolute values. Okay, so let me stop here for a second to see if there are like any questions that show up to this point. Is it making sense how I'm manipulating everything? No, the contraction, so the contraction is the name that you give to the function. You're saying that x squared is or I mean, a contractive function, I guess, because like the idea is that it will shrink the distances. What you need to provide when you say that it is a contraction is the constant by which it contracts. Okay, so that's what I'm trying to find. I'm trying to find by what factor it kind of like shrinks the distances, right? Which I still haven't written down. I still don't know by what factor it shrinks the distances. That's what I'm trying to find, right? If that makes sense. So, but you would call like the function like a contraction. But whenever someone says, "Oh, this function is a contraction," they also have to provide for you the constant that takes care of shrinking the distances. You see? So here, but we're almost there because what can you say? What can you say about the sum of x2 plus x1, right? What can you say about this sum? How much can that be? Notice that x1 and x2 are both on the interval 0 to 1/4, right? The 2 points are always on this interval. So when you add them, right, what is the most that this number can become if you're adding 2 points between 0 and 1/4? What would be the maximum? 1/2, right? 1/4 plus 1/4. Okay, so this is the key part, right? This is where like the analysis is in. So this is 1/4 less than 1/4 plus 1/4, and that is where I'm using the hypothesis that I'm looking at the interval 0 to 1/4. You see, uh, so what we just found is that if you take, so what this is saying is that x2 squared minus x1 squared is less or equal to 1/2 times x2 minus x1. Here, this is because um, uh, we're on the interval. And so the contraction is 1/2. So what that means is that you can take 2 points on the interval between 0 and 1/4, and when you square them, the distance between the squares is always at least half. It cannot exceed half the distance of the original 2 points. So this is like the contraction factor. Is that making sense? and so, but you see, it's kind of like a game because first you have to think about the function, and then you also have to think about the interval. Because if I had made the interval too big, right? Imagine I have made the interval 0, 1, right? Where I say, oh, the points can be on the interval 0 to 1, right? Uh, if I had extended this interval to 1, then this argument completely fails, right? Oops, sorry about that. Then this argument is a complete failure because if you put 1 plus 1, right? If you put 1 plus 1 here, you get 2. And 2 is not a contraction, right? Like you're just saying that the distance of the squares cannot exceed twice the distance of the original numbers, but the contraction really wants to shrink it. So kind of like I'll tell you more about this you know tomorrow. But the idea in the fixed point theorem is that you want to focus on a function that is a contraction on a particular interval. Okay, with some other thing, but that's like not that I mean it's important, but it's not as important as being contraction. And once you have a function that is a contraction on a closed interval, then you can kind of like create a sequence that will converge to the fixed point. That's kind of like the cool thing, which I'll tell you. Oh yeah, yeah, no, like it could have been. Sorry, it could also be negative numbers. So it is also there's nothing of what I said that wouldn't have been an issue. Like with if you had chosen like for example, what let's actually leave it for you to check. So check that this works. Like let's put it like as a check. So check that the same function, right? Is also a contraction, also a contraction on what? Let's say on the interval negative 1, 6 to what I want. Let's say, I mean, it doesn't have to be symmetric. I don't want you to think that it's symmetric or something like that. It's almost like the exact same argument, but I just wanted to an interval that would also include like negative values. Well, no, that's a great question. This is because it's related to x squared. But if you had chosen something else that is not related to x squared, then the interval could be outside like negative 1 and 1. You see, like for example, imagine this may seem a bit stupid, but imagine if I had put something like uh, you know, like here's another one. Imagine if I had put like something like 1 over 100 times x squared, right? Like definitely that's going to be a contraction in a larger interval. You see what I mean? Let's say like that one probably like if you like let's say like negative 2.5 just to so that you'll see it. Because like the factor of 100 kind of like will shrink even more like everything. You see what I mean? So it is like a game, right? It's not, you do have to look at the specifics of the function, right? So it doesn't Uh, but and that's what actually we'll talk about tomorrow. So kind of like the key tomorrow is to look at the derivative. If the derivative of the function doesn't grow that fast, then you can kind of like um, show that the function is a contraction on a particular interval. That's kind of what I'll start doing tomorrow. So tomorrow I'll start with that. Once we have that fact, then kind of like I can show like the fixed point theorem that constructs a sequence that converges to a fixed point of the function. But that's kind of what I'll do tomorrow. I think this is like a good place to end. I'll add some more problems on the notes, including some of showing that certain functions are contractions so that you get some practice with that because it's kind of like a cool thing to kind of like work with around because it's kind of like a little bit of trial and error, which is always like fun because if you find like there can be more than one constant that works, right? So you can sometimes try to find the optimal constant and things like that. But we can yeah, I'll add some of those tomorrow. So if that sounds good, let's end here. And I'll kind of like pause the recording, but I'll stay around if someone wants to ask me anything specific. If not, I'll see you tomorrow. I see you too.
Um, I have a quick question about the practice problems.
Mm-hmm.
Um, so I was wondering, is there like an answer key for it, or is like after you do them, we can like
I mean,
after
some of
some,
them do have answer keys right now. Wait.
wait, where do I find the answer keys? Are they on the same
Yeah, it's right
page?
below the problem. It's just like wait, sorry. This is like the loads, not the problems. So like to the extent that it's possible, like like there's certain problems where if I were to put the answer key, then there's nothing to ask. You know what I mean? But for example, if you look here at problem 1.2,
Mm-hmm.
it's AB and then it says ans. So
Wait,
there,
where?
like right below, you see? Like, can you see? Like, I'm sharing my screen.
Oh, okay, sorry.
Yeah, yeah. Do you see where it says ants?
Uh, oh, okay, sorry. I didn't really see it very well. I thought that was like part of the problem. I'm so
Yeah,
sorry.
yeah. I kind of tried to hide it a little bit to be a bit more discreet. But I mean, so for those which are kind of like numerical, I'll put like an answer key. There's some which like here's like one actually in the bisection method. Okay, like this one that says like, can you use the bisection method for sine of x plus one, right? Um, for this question. Like if I write the answer, I basically have done the problem for you. You know what I mean? So I cannot
Right.
put the answer, but you can ask me about it. But what would be the answer there? Like, if you remember, like for example, sine is always between -1 and 1, right?
Mm-hmm.
And so if you add 1 to sine, that is never going to be negative, right? Uh, Sine of x plus 1 is never negative, if that makes sense.
Mm-hmm.
And so you cannot apply the bisection method because the bisection method requires, you know, the endpoints to have different signs, if you know what I mean.
Okay.
Yeah, and so like, it's not too bad, but like it does require some thinking. But if I just put no because, if I write on the answer, if I write like an answer key for that one which says no because sine of x plus 1 is never negative, they kind of like I did it like, then it's kind of like not the same because then like it's very easy for someone to just read that and never thought about it. So but if it's one more like, oh, what is like the approximation that you get in the bisection method at step 7 or something dumb like that, then yeah, I'll put what you should get, um because that way you can just check it. When it's like numerical or you just have to compute things, then yeah, I will put those on the
Okay.
answer. Yeah, yeah, under
Yeah,
answer key.
because
And for
like yeah, because I just only had like a quick glance at it, so I didn't really like really read the questions. So
yeah,
I
yeah,
haven't
yeah.
done them yet, but I plan to like do it like today or like
I mean, for
during
now,
my free
like,
time.
yeah, like, I mean, for like at least for tomorrow's quiz, like as I said, I will base it on just like the first two problems. But yeah, like I think you probably can already take a look at some of these bisection questions. I believe you should be able to work on all of them right now. And then I'll add over the day like some more. So but yeah, my approach will be kind of like if it's completely numerical, then yeah, I will put the answer key. And if it's one where if I write the answer, then there was nothing to do, then yeah, I wouldn't put it like directly, and then you would just have to like ask me if you're still having questions about that.
Okay.
Yeah, yeah.
Thank you.
Okay, sure.
Have a nice day.
You too. Too. Anyone else?
Um, uh, Hi, can you hear me?
Yes.
Yeah, so I also had a question about the practice problems.
Mm-hmm.
Uh, I don't know if I'm missing it, but do we have to like upload the answers to it or something like
Uh,
that?
I may create some assignments, and when I create the assignment, I may ask you to upload specific questions, but not to all of them. So right now I haven't made any assignments, but yeah, like probably by the end of the week, once I have added some more problems, I'll be like, okay, upload solutions to problems 3, 4, and 5, to just say an example. But in
Mm.
the meantime, you don't need to upload anything. Yeah,
Okay, so you'll specify.
I will specify, and I wouldn't ask you to upload solutions to all of them. That would take forever. So like, I'll just select some important ones. Uh,
So like these are just for practice, for now.
Yeah, 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 yeah. This is just like for you to have like like I'll base the exams on these, and that's it. Like
Sure,
so, if you go through them, then the exam will be not a surprise because like most likely I'll change like just like the number to some of these questions, and that's the exam.
sure. Thank you
Yeah,
very
yeah,
much.
yeah, sure.
I just had a quick question about 1.3 on this.
Of the Cauchy one? Yeah.
Yeah, I don't really understand A. Is there any way that you can kind of go over that?
So let's see. Find the n. Oh, okay. What is the sequence? Did I write that? Oh, I wrote the sequence as 1/n. So let me see if I can share my tablet again. Uh, Let me use a different like files just that it doesn't. Okay, let's say it was 1.3, right? So like I gave you like the sequence is 1/n, right? Um, okay, and the idea of like being Cauchy, well, here I'm giving you the epsilon, right? Epsilon is 1/2. Um, so basically, uh, being a Cauchy sequence means that you have to find, so you have to find an index, right? A number n with the property that if you take two elements of the sequence beyond that index, right? They're within distance epsilon, right? So in this case, they're within distance 1/2 from one another. Whenever n and m are greater than n. Is that making sense? So basically, you're trying to find an index. Like you want to say like it is the 10th element in the sequence, right? After you consider the 10th element in the sequence or anyone after it, the elements of the sequence are always less than a distance of 1/2 from one another. Okay.
Hmm.
So what does that translate you to this in this particular example? Well, in this example, the sequence is 1/n minus 1/m, right? So you need that to be less than 1/2. So this is what I want, right? But what can you say? What can you say about the distance here? So the idea is that you can say, I mean, this is kind of like one of like these things how like absolute value works, right? Uh, the like the property of absolute value is called like the triangle inequality sometimes. Is that the triangle the distance between the 2 points is just like less or equal to the absolute value of you know each of the terms. Is that making sense?
Okay.
And then, but what can you say about 1/n, right? Again, what you have to imagine is that like the index, you don't know what the big M should be, but these two should be beyond that element n. So because these are bigger integers, because they're bigger integers, their reciprocals will be less than 1/n. So each of them would be less than 1/n plus less than 1/n. Okay. Is that making sense? Because again, like you still don't know what big N is. Like I still don't know what it is, but this is supposed to work for any two integers bigger than that number. Okay. So if say for example, if this is 10, this could be 20 and 30. So 1/20 and 1/30 would be one less than 1/10. Okay. Like that's how the reciprocals work. Because like when you take reciprocals, like the inequalities flip. That's what I'm trying to say.
Hmm.
Okay, so this is 2/n, but that is if you make this less than 1/2, then that would guarantee that like the difference between these two numbers is less than 1/2. So this gives if you want this to be less than 1/2, that tells you that n has to be greater than 4, and that's how you get that n could be 5, for example. You see,
Okay.
it's kind of like calling in reverse. You kind of like play with what you want to get. You want to get to that being less than 1/2, right? Like the
Yeah.
distance between the points. And so, if I know that the distance between the points have to be less than 1/2, how big should the index be? Like, how big should this integer be? So you kind
Hmm.
of like reverse engineer. You see.
Hmm. Okay.
And the other one, if it's not one half, you just put epsilon, right? But it's kind of like the same idea. Then you just solve for epsilon here. Instead of one half, you would put one like epsilon, and that gives you that 2/n should be less than epsilon, and that's why I wrote there that for part B that you could take n to be any integer bigger than 2/epsilon. That's where it comes from.
Okay. Okay, that makes
I, I
sense.
I mean, I guess I won't ask anything about the Cauchy sequence like everywhere, but it's just for people to kind of like at least see it once, so that you have like an experience of how like these arguments go. I like for like an actual sequence, like kind of like 1, 2, that's fine. That's a little bit more like straightforward. So I think that's kind of like a bit more easy to work out. But the Cauchy sequence is important just because what's nice about it is that you don't need to know the limit ahead of time. You see, so
Hmm. Okay.
that's
And
that's what
then
makes it cool.
yeah, and then one last question. Are the homeworks going to be assigned on that textbook thing, or is it going to be like a
Well, I'm
Canvas
copying.
assignment?
I would be. I mean, I'm copying some from the textbook, but I'm copying some of the problems from other places. So, if I give a homework, it will be from this PDF.
Okay, so do we need the textbook, or can I just like find a free PDF online?
I mean, if you find one, and yeah, and that's fine, then yeah, like I won't ask anything directly from the textbook. Yeah, yeah.
Okay. All right. Awesome. Sounds good. All right. Thank you.
Yes, yes. Fine. Do you have a question, Lillian, or? Okay.